All right, so they asked me to do a basics of concrete, and so when I sat down and think about this, I figured that most every one of us probably had some type of concrete materials course in class, and I figured you guys all know the difference between cement and concrete, so I wouldn't cover that type of stuff. But if you don't, come see me, and we're gonna have a long discussion about that topic. So that's one of my pet peeves. So I tailored this to more of a concrete durability aspects, and since we're always looking for long life out of our structures, durability is the thing that we really want to kind of focus on, and our specifications are highly geared towards durability as well. You may not know why they're there, but that's really why they're there, is we want long-term durability. All right, so first poll question, what is your current role? I think we kind of had a similar question, so we could probably see that most of us are going to be text dots. I guess all the industry left. Man. There we go, a few material suppliers, consultants. So just to give me a sense of what the room is here, so. Good. All right. Next question. How would you rate your concrete materials knowledge? You consider yourself a guru, somewhat, enough to be dangerous, non-existent because you're a hot mix guy. All right, I get to teach some hot mix guys some things, so. All right, you concrete gurus, you're going to want answering all the questions. So if you answer you're a guru, be warned. All right, next one. Have you ever produced, inspected, tested, or even dreamed about concrete? Hey, I was afraid I was the only one. Man, I'm glad. All right, there's a bunch of sick minds in this room, I guess. 20% of us dream about concrete. Awesome. All right. In your current role, do you think about concrete durability? Well, that's good. A pretty good percent of us kind of think about durability during our jobs. I would not have expected that, so I'm actually glad to see that percentage is pretty high. All right, in your opinion, is concrete durability in Texas an issue? Kind of what I thought would be the results here. I think we have some regional issues, and I think yes, we've had some durability issues that hopefully most of our specifications have solved. But I think we're still there's room to improve. But I think most of our issues are probably regional. You know, the colder climates and coastal areas, things like that. So. All right, so when we talk about durability, what mechanisms are we trying to prevent? And these are just kind of the main ones that most DOTs are trying to combat, with corrosion probably being the number one. If you look nationwide, that is the one that everyone is trying to not have, because it definitely shortens the life of our structures. But in Texas, we've had a significant issue with alkali-silica reaction. We don't really have a carbonate reaction issue, but that's one of the ones that other DOTs are dealing with. Delay etching formation. Anyone ever heard of that? It's a less common guy, so but I'll kind of cover that a little bit. Freeze-Thaw is a big one that a lot of our northern DOTs deal with. Some in Texas. Scaling, that's another de-icing freeze-thaw issue. And then external sulfate attack. So these are just kind of the handful of durability issues that most concrete guys kind of look at of trying to prevent. All right, so next question is, what do all these deterioration mechanisms have in common? Take a best guess. What is the one thing they have in common? Don't be shy. You're not getting graded. failure. Okay. Okay. Guess that's the topic of the presentation, huh? All right, all those have their common things. Well, who said water? Raise your hand. Who said water? We're back there. That is actually the right answer. Water is the one thing that all these have in common. That we're trying to control water, and so if you stop that, then you probably get rid of most of these deterioration mechanisms. So I'll let you on a little secret, okay? We control water ingress, we control these durability mechanisms. All right, so easier said than done, especially in transportation structures. Most of them are in water, some are in water, it rains, right? So it's kind of hard to do. So how do we do that? Well, we have to look at with most things, kind of the entire approach. We have to look at the environment, where our structure is going, any design aspects we have to consider. Do designers even consider durability as they're going through this process, right? And then we get into kind of the materials and proportioning, curing, all with the goal of trying to minimize cracking, right? You stop cracking, then you're already ahead of the game. But if we have decks that crack, we're setting ourselves up for failure, right? So this is probably, I could talk probably all day about this, probably 3 days, a month. So I don't have enough time. I'm only going to focus on a few of these yellow boxes here to kind of just give you an idea of what we do as far as durability. All right, so a few material considerations for durable concrete, and then the first issue we're going to talk about cement and SEMs. And again, everyone knows what water-cement ratio is, right? It's our weight of water per our weight of cement, and that's our main parameter that a lot of people are familiar with. And it tells us some degree of strength and durability. So that's going to be one topic I'll discuss, and then other things like chemistry of materials and proportioning. All right, you are warned. There is going to be some chemistry involved in this presentation, and you will be required to remember at least one of them. And you will be tested at the end, so keep that in mind. All right, so water-cement ratio, and really in the terms of this presentation, I'm talking about permeability. We got a few concrete guys in here. Who has ever measured permeability, and I'm not talking the rapid methods? Who has ever done that? And I just said the most important thing is keeping water out. And no one here has ever measured permeability. So why? And this is kind of what permeability is, right? Flow of water through concrete. We're trying to minimize that. So why don't we do that? We don't want to end up like this guy, right? This probably has to be the boringest job ever, watching that little tube and how much water is flowing into that concrete. But it's a very important parameter of concrete, and if we stop the water ingress, we will stop most of our deterioration mechanisms. But again, I can't imagine doing that all day. All right, so in terms of permeability, what we're looking at. So this is a high water-cement ratio concrete. A little depiction here. I think I have a laser. Cement particles in some water. The higher the water-cement ratio, the further the particles are from each other. They're basically diluting the system. But we're also creating these larger pores that are connected to each other now. That's the path for water to come in when it dries. When we talk about lower water-cement ratio mixes, well, now our cement particles are closer together. We have less connectivity of the pores. Therefore, the ability for water or other ions to get in is reduced. Okay, so that's what the goal is in terms of trying to set a lower water-cement ratio is really for a permeability issue. All right, so here's some data showing water-cement ratio versus permeability. Again, there is some large spread, meaning there's other factors that control permeability. However, water-cement ratio is a fairly large lever arm in terms of permeability. We could get some substantial reductions in permeability if we reduce the water-stream ratio slightly. What's our specification for max water-stream ratio for most concrete? We're at about 0.45 limit, right? So we're somewhere around here, right? So we lower that limit over the years to try to get more or less permeable concrete out there in our structures. We also get a strength increase with the lower water-stream ratio as well. That necessary isn't always a good thing, but it does come along for the ride. All right, so let's talk about cement chemistry. Again, here's where we get into the hardcore chemistry. These guys right here, these are the compounds of cement, these first set right here. These guys are responsible for strength, right? Those guys, when you mix with water, they're going to give you the glue that holds everything together. This guy is a bad guy, right? C3A. That's where our sulfate attack and our DEF issues come into play. So we have specification. So when you're in a sulfate environment, we limit the cement to a certain level of C3A. Okay, so that's in the specification. We know that and we control that. This guy basically makes concrete gray. That's basically all he does, right? Calcium sulfate plays a role when we start talking about sulfate attack and DEF. And then these guys are ASR guys. Those are the ones we want to try to limit as much as possible. But again, we're kind of stuck with the cement that is produced, so we have to find ways to not have ASR with those guys. So if you know a little about cement chemistry, you could try to figure out, what you can and can't do with that particular mix design. All right, this is probably one of my favorite plots of cement hydration. This basically tells you the life of concrete or cement hydration from 0 to about 90 days. So we mix with water, things really don't happen for a while, then all of a sudden, a couple hours later, things kick off. We start making glue, calcium silica hydroxide. We make some calcium hydroxide, some other stuff, ettringite, monosulfate. So all these reactions happen within the first hours and days of the concrete's life. Porosity, permeability, decreases as we start hydrating and getting lower. So this slide, I love it because it tells you basically everything you need to know. So as with everything, we need to have a goal though, right? Our goal for concrete hydration is to produce as much CSH as we can, reduce calcium hydroxide, and reduce porosity. So how do we do this? What do we do to achieve this goal? So here's your next question. Any guesses? What one thing can we do to solve or get all three of those goals achieved? This is a tough one too, so we'll see how good you guys are. There's at least one person in here that should answer it right. No pressure though. Beat the hell out of Florida, okay? Wasn't expecting that one. Wait. Fillers. That's along the right path. There you go. Fly ash. Fly ash or SEMs. And for Texas, most of the issue is we're a fly ash state. That's what we have. And here's a beautiful picture of fly ash. Brown spherical particles. They're made from byproduct of the power plant company. And so they sell this stuff, and it does wonders for concrete. It's amazing stuff. We love it. I want every cubic yard of concrete to have fly ash if I could. All right, so how does fly ash do this? Well, let's look at the reaction, right? So when you mix cement and water, so those are the strength guys, add some water, you get glue, and you also get calcium hydroxide. So what was their goal? Increase this guy, decrease that guy. So when I put fly ash in there, fly ash is basically this silica and aluminate content. They're going to grab this CH, use it in its reaction, and now I've made more glue, and I've reduced the CH. So I have achieved two of my goals already, right? By putting fly ash in there, I got two goals achieved. Now I got to work on the porosity. So where does the porosity thing come into play? All right, so let's look what happens when you use fly ash. Okay, so again, we use up that calcium hydroxide, and then we have this phenomenon of improving this transition zone, right? So if you look at an aggregate, that calcium hydroxide that is produced, it's plates. I don't know if you saw some of those presentations early on show those micrographs. So calcium hydroxide are these plates, these flat plates, and they line up along the aggregate. So this zone right here is very porous. So water comes in and it's going to find those zones and just trickle its way down through the concrete. So again, when we use fly ash, we use up this calcium hydroxide and we make more glue. So there we go. We have now improved the porosity of that region, and now that is more like the bulk paste out in the middle. So fly ash is very, very beneficial to concrete. Here's some data showing just that we have a substantial reduction in permeability over time when you have fly ash in the mix. All right, not fly ash is created equal. This is Class F fly ash. It is basically a silica based material, right? That's what we want. Class C fly ash is kind of more of a calcium oxide with some silica. It also has the glass chemistry is also different between the two. This has more calcium aluminate glass, that C3A glass that I said was a bad player early on. This one doesn't. This is more of a silica aluminate glass, right? So this is good for most durability aspects. This maybe not so well. Let's look at sulfate attack. Sulfate attack with Class C fly ash or Class F fly ash, very good, 20%. No expansion. Control had tremendous expansion. Let's put 20% C ash. Man, that's failed. More should be better. Here's 40%. That didn't get better because the chemistry of the glass of the C ash is completely different than the chemistry of the glass of the F ash. So we kind of have to know these things. And if you read our specification, we say no C ash in sulfate environments. So why do we do that? This phenomenon right here, because the chemistry of the fly ash is not set up to control that durability mechanism. Here's some research we did. This is actually some of my research that when I was in grad school. This was probably a month into the test. Completely disintegrated. This had a high calcium C ash in the mix. The F ashes went, 18 months. Here's some exposure blocks or prisms that were in a tank, and they completely disintegrated. So it's, we have evidence that that is a true phenomenon, right? C ashes don't behave well in sulfate environments. So just keep that in mind when producers come to you and say, hey, I want to switch my F ash to my C ash. Slow down there, right? We need to figure out what we're doing before we allow that requirement. All right, I talked about the layout transformation earlier on. It's a lesser of the mechanisms that we have in Texas. However, we still have it. It is a cement chemistry issue, but more of a early age temperature history issue. If we let things get hot too early, we don't allow the right products to form, and then we'll have issues down the road. And so basically what happens here, if we get this concrete temperature up above 160 degrees, our sulfates and our aluminates kind of get trapped in the hydration products, and they're not available to do what they normally do, okay? Okay, no big deal. It didn't happen the way we wanted it to happen. Okay, is that a problem? Well, in 10 years, it may be. Because as water comes into our concrete, because it's low permeability or whatever, these sulfates and aluminates get back into solution. They're like, hey, I want to go swimming, and they go into the pore solution. But they don't like being alone, so they have to find each other, and they make etchingite. Okay? Etchingite is a crystal that loves to grow big. Right? And so as this crystal grows and grows and grows, it exerts pressure. Concrete's not good in tension, and therefore we get cracking and substantial cracking. This is a structure. I couldn't find the picture, but we actually dug out the footing of this thing, and you could stick your hand in the crack. That's how big that crack, or how much expansion we actually had from DEF. Also in precast, it's been an issue because of high SAC contents, trying to get early age strength. This is a girder that would have gone to Houston, and you see all the cracking that developed. That girder just sat there. It's never been in service. So we have had these issues in Texas. All right, so let's switch our role to aggregates, right? So these are a couple of things. Anyone's ever heard of decracking? Okay. Don't have any in Texas that I'm aware of. which is a good thing. Other DOTs they fight this every day. So we're fortunate that we don't have decracking, so I'm not really going to cover decracking. All right, let's talk about ASR. So ASR, again, I think someone mentioned this early on, it's an alkali-silica reaction between the silica and the aggregate. That's an amorphous silica, and the alkali floating around in the paste. So you have these hydroxyl ions that make everything high pH. Those basically will dissolve the silica in the aggregate. That silica comes out into solution, reacts with the sodium potassium. When water enters the system, makes this alkali silica gel. Okay, no biggie. We got gel. You see ASR in probably everyday concrete. The problem is if that gel is expansive, it will grow, exert pressure, and then ultimately crack the concrete. All right. So again, this trying to avoid cracking the concrete is the main goal of any durability aspect. So does this really happen? Yes. Here are some aggregates from Texas concrete that has severe deterioration, a lot of ASR gel going on. Here's a prestressed girder. It's okay, no blackberries were harmed in this making of this photo. But if you're ever wondering what happened to all our blackberries, we fill cracks with them. So that's what we do. They didn't go to waste. But this is a girder in central Texas, around Austin, that is still in service, that has a pretty substantial crack in it. A lot of research was done on ASR deterioration, and this girder, even this severely cracked, still has enough capacity to carry load. But now you start getting into corrosion issues, and how long is that going to last? So, all right, so let's talk about how reactive our aggregates are. This is a plot of all our fine aggregates in Texas. 0.1 is generally the limit. We consider anything above that as reactive. Here's a few limestones. Hey, limestones have chert in them. I think Harry mentioned that early on, so that's the reactive component. But look at these guys, all our river sands. And I would question some of these down here. I don't know. That doesn't make sense, but everything's reactive. And TxDOT made a very good decision back in late 90s, early 2000s to say all aggregates are reactive, so everyone's guilty of being reactive, and you cannot prove your innocence. So I call it Texas law. You're guilty and you can't prove your innocence. So we have to mitigate. So how do we mitigate? Well, we can't use non-reactive aggregates because we probably don't have any, or they're not together, so that's not going to be realistic. Eliminate moisture. Large elements have enough moisture to drive the reaction. So if we seal, do all kinds of things to keep moisture out, there's enough moisture in there to drive the reaction. So we can't really do that. Some of our specifications limit alkalis. That's a good one. But again, use of fly ash and other ASTM combinations. And so if you look at our specification, we have 8 mix design options. All those mix design options are there to mitigate ASR. They're there for no other reason other than to mitigate ASR. So if you have a contractor saying, no, I don't want to use one of those options, you're running a risk that you're going to have ASR in your concrete down the road. It may not happen a year, 2 years, 10 years, but it may happen 20, 30 years down the road. We found a pavement down in Laredo that has ASR, and that pavement's 25 years old. And it cracked to hell, but it will happen. So be careful with modifying those mix design options. We've done a lot of work to make sure those options work. So just keep that in mind when they come up to you and say, hey, I don't have fly ash. Can I put 800 pounds of cement in there? Like, no, that's not what we want. You have to have the right amount of ash. Again, this is our F ashes. And hey, 20%, what's our minimum? 20%. So I mean, we just didn't pick that out of the air. We actually have some data showing that's where we need to be for ASR mitigation for most of our aggregates in Texas. Gradation is important. I am a well-graded guy. I love optimized graded aggregate. I think it does wonders for reduced paste content, reduces shrinkage, reduces cracking, so all that, helps. Versus gap graded, have a lot more paste to fill those voids. Permeability gets reduced because of the lack of paste. So, I mean, there's other benefits to having well-graded aggregates as well. Internal curing is a kind of a hot topic here nationally. I'm pushing to have, me and Bridge are pushing to have more of these things used. But basically what internal curing is you're actually using lightweight aggregate that has a lot of porosity. You saturate them, and then who's ever looked at concrete as it dries, right? That sheen of water, and then they say once the sheen of water disappears, that's when you spray your curing compound and things like that. Well, why does that water disappear? And most people think it evaporates, but no, that's the point in time where the concrete goes, hey, I want water, and it starts to suck it up, right? That is what's happening. Those capillary pores are now restricting, and they're going to pull that water from the surface because it wants water. Well, when that happens, that's when these aggregates come into play, and they say, hey, I got all this free water. I'm just going to give it to you now. And so when that concrete sucks up that water, now it has a source to suck it from. And so that's what happens with internal curing. Rather than trying to provide moisture from the surface, we're providing moisture through the entire bulk of the concrete. So I think this is going to be a huge step forward in improving our durability, especially in harsh environmental conditions, high wind, low water, low humidity, things like that. Again, there's a lot of data out there on IC. People have researched this stuff to death, so I don't think we need to research it anymore. We just need to implement. So a lot of stuff showing the benefits, less shrinkage of all types of things that were used with internal curing. So I really want to try to push this idea forward in the department. All right, now the big one, corrosion. Again, steel loves reinforced concrete, or steel loves concrete because of the high pH environment. We're about 12, 13 pH. However, if we start adding salts, or salts get down to the steel, we will start to corrode. Or if carbonation occurs in our concrete, we will also get some carbonation corrosion occurring as well. All right, so a couple of the protection strategies. Don't use chloride, de-icers. Well, our policy right now is to use brines, and so I really worry that we're setting ourselves up for a huge issue because we're going to be putting these brines on our decks, especially our older decks that were built 30, 40 years ago, that we weren't thinking about long-term durability back then. We weren't using fly ash. We weren't thinking about all this stuff, and so now are we going to have issues, right? So that's going to be, time will tell what happens there. We use membranes to seal them. However, those become issues with skid and how well do those membranes last, things like that. Those tend to keep chlorides out. Again, most of our spec is trying to focus on low permeability, fly ashes and lower water-stream ratios, things like that. So that's kind of where we have kind of driven our specification. Epoxy coating, steel, stuff like that, we use those in several districts. Non-corrosive materials, FRP bars, stainless steel, some of those things. We've used those from time to time. Chemical corrosion inhibitors. Some of our bigger structures, marine structures, have gone that route, adding 2 or 3 gallons of CNI in the concrete. That also buys you some time for corrosion. So there's a couple different things that we could do for mitigating corrosion. But again, the first step is getting non-cracked concrete, right? For low permeability, non-cracked concrete is probably the easiest thing to do, and that's kind of what our specification tries to focus on. All right, carbonation corrosion. This is an interesting slide. We have curing days versus percentage of fly ash. As you see, as fly ash increases, you increase your depth of carbonation. Why? Because fly ash consumes calcium hydroxide. Calcium hydroxide acts as a buffer for carbonation. So we're doing something good, but we're kind of doing something bad for carbonation. But the saving grace is, well, if I cure, then I have less carbonation. Look at the difference between 28 days of curing versus that. So the main takeaway here is cure your concrete, but cure it properly. We want this nice, even, white coating of curing compound. The best specification I ever read for curing was from Minnesota, and it said, the curing compound shall be as white as a blank sheet of white typing paper. It had nothing about rates, had nothing about number of coats. It was just make the damn thing white, okay? What we don't want is this. Who's seen this? All right, I was on a project last week and they were pouring sidewalk. And this is what we saw. I have done nothing here for curing, right? So if you see this on your project, that is not acceptable. Because they're doing it with sidewalk, they're doing it with riprap, they're doing it with rail, they're doing it with paving, they're doing it with everything. So this is not acceptable. So I'll get off my little soapbox right now, but we want this, we don't want that. All right, Freeze-Thaw. This is kind of the classic image that everyone shows, Freeze-Thaw durability, and kind of the deterioration that happens. Where are my beer drinkers? Oh, come on, I was out last night. There's more of you in here than that. That's right. What happened here? You fell asleep, and your wife woke you up in the morning screaming, "What did you do to my freezer?" Right? You left your beer in the freezer, and it busted, right? So why? Well, same thing that happened with your beer bottle will happen in concrete. As the concrete gets saturated, it freezes. Water has to go somewhere, so it tries to go all through all the little pores, creates pressure. That pressure ultimately cracks the concrete. That's basically what happens with freeze-thaw damage, right? And it's at layer, so the first layer will start cracking, and then you just start going lower and lower and lower. All right, so how do we resist freeze-thaw resistance? We use air entrainment. We purposely put very small bubbles in the concrete, so that way when the water freezes and it has to go somewhere, it has a place to go. It will fill up these voids and not create the pressure that we would normally create if we didn't have air entrainment. Pretty simple. The problem is trying to get the bubbles at the right space, and I can tell you air content isn't always the best way to measure freeze-thaw durability. Because you can have coarse air, 5%, but your spacing factor is way off. So people are working on trying to measure fresh or spacing factors in fresh concrete. And I think they're close. I think we're doing it now. So that's something that we will probably look at in the future here of implementing as well. All right, so big question I always get is, hey, do I need air? I'm in Fort Worth. Do I really need to put air in my concrete? And that's a question we've been getting for years and years and years. And the guidance that we have been giving is anything north of I-20, use air. Anything south of I-20, don't use air. And I always find it odd that these guys always use air. I'm like, well, why are you using air? They're selling you air. Why are you using air? And it can cause problems, but they've been doing that way for 30 years, so they like using air. Okay. But we don't have very many freeze-thaw cycles, and the important thing about freeze-thaw cycles, they need to be wet freeze-thaw cycles, right? We need to have moisture to drive the freeze-thaw deterioration. And so we don't have very many, but we do have some. So the question becomes when you get into fly ash. I want fly ash in my concrete, but there's an issue that the unburnt carbon in the fly ash consumes the air entraining admixture. And therefore, you're moving along, you're going fine, then you get a bad load of fly ash, and it kills your air. So then you start dumping more air entrainer in there to get your air back up. Well, your next load of fly ash is good, and boom, you got 10% air, and your strings tank. And so we're always chasing this air content issue. So, so you northern districts really have to figure out, do I want fly ash, do I want air? The fly ash industry is working hard to try to treat ashes, so that way they don't have this air issue. But the problem is going to be when the power plants start using activated carbon for mercury emissions. This stuff is so porous that it will consume all your air entrainer. My hope is that they will only have to use a very small amount, and then that now things become consistent. We don't have these fluctuations of unburned carbon. We know exactly the level of air entrainment we would need. So we'll see. Time will tell on that. They're still kind of working on these emission requirements. So the next couple of years, we'll really see more activated carbon in all our fly ash. All right, so that's all I had. My wife's a teacher, and we always sit down at dinner table, and she asks the kids, what was the one new thing you learned today? And so that's the question that we always try to, tell our kids, like, hey, we want you to learn at least one thing a day. So here's your chance. It doesn't have to be with this presentation, If you learn anything of the course of the day or even the conference, feel free to write it up there. But I just want to see if we imparted any knowledge on you guys today. Hey, I like that one. Cure, cure, cure. Good. Whoa, whoa. Someone wasn't listening. Who was that? We can find out who said that. All right, you guys were listening. I always worry that I just get glazed eyes and no one's paying attention. So, oh, that's my favorite right there. Awesome. All right, well, if you guys have any questions, I got a few minutes, or if you want to leave early, it's up to you. All right, thank you.